And now this red splotch that you see there, that galaxy, that's a galaxy.
No one could say how big the universe is. It's beyond the decillion of stars that a machine can reach, like the James Webb Telescope detecting red dots originating from the early universe. It's not the usual dots you see in books. The dots are terrifying, that humankind needs to know what's in it, what lives in it, or perhaps whether the dots are a part of a more massive astronomical body. It's time we know more about these mysterious circles. First, light years. In order to understand that the red dots were of course seen really tiny through the telescope, but in reality, these dots were monstrous and galaxy-sized.
All these little dots are galaxies, some of which are bigger than our own.
We need to comprehend the concept of light years. A light year is a unit of distance used in astronomy to measure the vast expanses of space. It represents the distance that light travels in 1 year in a vacuum. Since light moves at a speed of approximately 186,282 miles per second, or 299,792 kilometers per second, a single light year equals about 5.88 trillion miles, or 9.46 trillion kilometers. This measurement helps astronomers describe the enormous distances between stars, galaxies, and other celestial objects. The term light year can sometimes be confusing because it includes the word year, but it refers to distance, not time. For example, when astronomers say a star is 10 light years away, they mean the light we see from that star has taken 10 years to travel to Earth. This also means we are observing the star as it appeared 10 years ago, making a light year a useful tool for understanding not only distance, but also the history of the universe. Light years help put the scale of the cosmos into perspective. For instance, the nearest star to Earth, Proxima Centauri, is about 4.24 light years away. Meanwhile, our galaxy, the Milky Way, spans roughly 100,000 light years across. Beyond that, the Andromeda Galaxy, our nearest galactic neighbor, is approximately 2.5 million light years away. So, to give context for the next information to come, a light year is a unit of distance that reflects the immense scales of the universe, allowing astronomers to describe and explore space in a meaningful and relatable way. Now let's talk about how far the James Webb Telescope could reach. The ultimate telescope. The James Webb Space Telescope, or the JWST, is an advanced space telescope specifically engineered for infrared astronomy. As the most substantial telescope currently in space, it is outfitted with high-resolution and high-sensitivity instruments, enabling it to observe celestial objects that are too ancient, distant, or faint for the Hubble Space Telescope. This capability facilitates research across various domains of astronomy and cosmology, including the observation of the universe's earliest stars, the formation of initial galaxies, and the detailed analysis of the atmospheres of potentially habitable exoplanets. Despite the Webb's mirror being 2.7 times larger than that of the Hubble Space Telescope, it achieves images of similar sharpness due to its operation within the longer wavelength infrared spectrum. The longer wavelengths necessitate a larger surface area for information collection, whether through mirrors in the infrared range or antennae in the millimeter and radio frequencies, to produce images that match the clarity of those captured in the visible spectrum by the Hubble. The Webb was successfully launched on December 25, 2021, aboard an Ariane 5 rocket from Kourou, French Guiana. It reached its designated location, a solar orbit near the Sun-Earth L2 Lagrange point, approximately 1.5 million kilometers or 930,000 miles from Earth, in January 2022. The first image from the telescope was made public on July 11, 2022. The design and development of the Webb was spearheaded by the US National Aeronautics and Space Administration, NASA, in collaboration with two primary agencies, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The NASA Goddard Space Flight Center in Maryland oversaw the telescope's development, while the Space Telescope Science Institute in Baltimore, located on the Homewood campus of Johns Hopkins University, manages its operations. Northrop Grumman served as the primary contractor for this ambitious project. But why named Webb? The telescope is named in honor of James E. Webb, who served as the administrator of NASA from 1961 to 1968. overseeing the Mercury, Gemini, and Apollo missions. Unlike Hubble, which operates in the near-ultraviolet and visible spectra, as well as near-infrared, Webb is designed to observe a lower frequency range, extending from long-wavelength visible light, which is red, to mid-infrared. To prevent the infrared light emitted by the telescope from interfering with the light it collects, it must be maintained at extremely low temperatures, below 50 K. Its 5-layer sunshield serves to protect it from heat generated by the Sun, Earth, and Moon. The initial designs for the telescope, originally referred to as the Next Generation Space Telescope, commenced in 1996. In 1999, 2 concept studies were commissioned, anticipating a launch in 2007 with a budget of $1 billion. However, the program faced significant cost overruns and delays. A substantial redesign was undertaken in 2005, with construction concluding in 2016, followed by several years of rigorous testing, culminating in a total expenditure of $10 billion. Webb serves as the official successor to the Hubble Space Telescope, HST, and, due to its primary focus on infrared astronomy, it also follows in the footsteps of the Spitzer Space Telescope. Webb is anticipated to significantly exceed the capabilities of both telescopes, enabling the observation of a greater number of stars and galaxies, particularly those that are much older. The ability to observe in the infrared spectrum is crucial for this achievement, as it accounts for cosmological redshift and effectively penetrates the dust and gas that obscure visibility. This capability facilitates the observation of fainter and cooler celestial objects. Ground-based infrared astronomy faces limitations due to the strong absorption of infrared radiation by water vapor and carbon dioxide in the Earth's atmosphere, which restricts observations to specific wavelength ranges where atmospheric absorption is minimal. Furthermore, the atmosphere emits infrared radiation, which can often overshadow the light from the observed objects, thereby making space telescopes more suitable for infrared observations. The apparent youth of distant objects is a result of the time it takes for their light to reach observers on Earth. As the universe expands, the light from these objects becomes red-shifted, making them more detectable in the infrared spectrum. Webb's infrared capabilities are expected to allow it to peer back in time to witness the formation of the first galaxies, occurring just a few hundred million years post-Big Bang. Infrared radiation is capable of traversing regions of cosmic dust that scatter visible light more effectively. Observations conducted in the infrared spectrum enable the exploration of objects and areas of space that are obscured by gas and dust in the visible range, including molecular clouds where stars are formed, circumstellar disks that lead to planet formation, and the cores of active galaxies. Cooler celestial objects, characterized by temperatures below several thousand degrees, predominantly emit radiation in the infrared spectrum, as articulated by Planck's law. Consequently, many entities that are cooler than stars are more effectively analyzed through infrared observations. This category encompasses the clouds of the interstellar medium, brown dwarfs, planets within our solar system and beyond, comets, and Kuiper belt objects, all of which are set to be examined using the Mid-Infrared Instrument, MIRI. Significant missions in the field of infrared astronomy that contributed to the development of the James Webb Space Telescope include Spitzer and the Wilkinson Microwave Anisotropy Probe, WMAP. The Spitzer Space Telescope highlighted the critical role of mid-infrared observations, particularly in studying dust disks surrounding stars. Meanwhile, the WMAP probe provided evidence that the universe was illuminated at a redshift of 17, further emphasizing the significance of mid-infrared data. Both missions were launched in the early 2000s, coinciding with the formative stages of Webb's development. The next discoveries might wreck the nerves out of you, but we'll try to understand how gigantic, maybe colossal or astronomical, the galaxies were seen. Take note, it was just a telescope, but had the capability to peek through the dots. Red monsters, not dots. In the 2 weeks following the initial release of images from JWST,
in a statement, NASA said in just 1 year, the telescope has delivered on its promise of revealing secrets of the universe.
Several preprint studies emerged detailing a diverse array of high redshift and exceptionally luminous galaxies, which are believed to have formed between 235 million years and 280 million years after the Big Bang. much earlier than previously documented. On August 17, 2022, NASA unveiled a comprehensive mosaic image composed of 690 individual frames captured by the near-infrared camera NIRCam on the JWST, showcasing numerous very early galaxies. Among these early galaxies, Ceres 93316 stands out, with an estimated redshift of approximately Z equals 16.7, indicating its formation around 235.8 million years post-Big Bang, positioning it as a candidate for high redshift galaxies. In September 2022, the hypothesis of primordial black holes was introduced to account for the unexpectedly large and early galaxies observed. By May 2024, the JWST identified the most distant known galaxy, designated JDES-GS Z14-0, which is observed at a mere 290 million years after the Big Bang, corresponding to a redshift of 14.32. This discovery, part of the JWST Advanced Deep Extragalactic Survey, JDES, reveals a galaxy that is significantly more luminous and massive than anticipated for such an early epoch. Comprehensive analyses utilizing the JWST's NIR spec and MIRI instruments have uncovered remarkable characteristics of this galaxy, including its substantial size and dust content, thereby challenging existing models of early galaxy formation. Terrifying? Perhaps. The possibilities are endless. No one knows what's in these galaxies. Is it livable? Are there unknown species in there? The questions are endless, indeed just like the limitless universe. First, full-color images. Still, for so many people, the Big Bang is still a theory. These pieces of evidence might convince that there was really an incomprehensibly enormous explosion. The inaugural full-color images and spectroscopic data from the James Webb Space Telescope were unveiled on July 12, 2022, signifying the commencement of its general scientific operations. On July 11, 2022, US President Joe Biden presented the first image, known as Webb's first deep field. The subsequent releases around this period, including few amazing images. Carina Nebula, a young star-forming region designated NGC 3324, located approximately 8,500 light-years from Earth, which NASA has referred to as cosmic cliffs. WASP 96b. This release featured an atmospheric analysis revealing the presence of water vapor surrounding a giant gas planet situated 1,120 light-years away from Earth. Southern Ring Nebula. This image depicted clouds of gas and dust ejected by a dying star, located 2,500 light-years from our planet. Stephan's Quintet, a striking visual representation of 5 galaxies, where colliding gas and dust clouds are facilitating the formation of new stars. The 4 central galaxies are approximately 290 million light-years distant. SMACS 7327. This galaxy cluster, with a redshift of 0.39, showcases distant background galaxies whose images are distorted and magnified due to gravitational lensing effects caused by the cluster. This particular image has been referred to as Webb's first deep field. Notably, it was later determined that this image also revealed 3 ancient galaxies that existed shortly after the Big Bang, providing a glimpse into the universe as it was 13.1 billion years ago. What a remarkable discovery and feat to unfold the early universe, as old and aged as the Big Bang. On July 14, 2022, NASA unveiled images of Jupiter and its surrounding regions captured by JWST, which included infrared observations. In a preprint published around the same period, scientists from NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, reported that, almost universally, the scientific performance of JWST has exceeded expectations. The document detailed a range of observations conducted during the commissioning phase, during which the instruments successfully recorded spectra of transiting exoplanets with a precision surpassing 1,000 parts per million per data point, and monitored moving objects at velocities reaching 67 milliarcseconds per second, more than double the specified requirement. Additionally, it captured the spectra of hundreds of stars simultaneously in a densely populated region toward the galactic center of the Milky Way. The Big Bang and the inactive universe left behind. To be clear, JWST has identified enigmatic little red dots in the early universe, dating back approximately 13.2 to 12.2 billion years. These compact, red-tinted galaxies challenge existing models of galaxy formation and black hole evolution. Many of these objects exhibit broad emission lines, indicating the presence of active galactic nuclei, or AGN, powered by supermassive black holes. However, their characteristics, such as flat infrared spectra and weak X-ray emissions, deviate from typical AGN profiles, suggesting unique formation processes in the early cosmos. The discovery of these little red dots compels scientists to re-evaluate their understanding of the early universe's structure and the rapid development of massive celestial bodies. The Big Bang, which occurred approximately 13.8 billion years ago, marks the origin of the universe, an event of immense energy and expansion that set the stage for the formation of galaxies, stars, and planets. However, the aftermath of the Big Bang also left vast regions of the universe inactive and seemingly devoid of activity. These inactive areas, often referred to as cosmic voids, are regions with significantly lower densities of matter compared to the surrounding cosmic structures. While not entirely empty, these voids lack the gravitational pull needed to draw material together and ignite star formation, leaving them relatively quiet compared to the bustling centers of galaxies and clusters. These inactive regions provide unique insights into the nature of the universe. They act as a counterpoint to the dense, active areas filled with galaxies, offering a clearer view of dark energy and dark matter, which dominate the cosmos. Studying these voids helps scientists understand the large-scale structure of the universe.
Is that we did not...
7,000 in this picture?
The size of this field is, if you...
revealing how matter is distributed and how cosmic evolution unfolds. Furthermore, the inactivity in these regions underscores the role of gravity in shaping the universe. Without sufficient gravitational interactions, the matter remains dispersed, preventing the formation of stars and galaxies. Despite their quiet nature, these inactive areas are crucial to understanding the universe's overall behavior. They highlight the dynamic interplay between expansion, gravity, and the clustering of matter, illustrating the complexity of the cosmos that emerged from the singularity of the Big Bang. In this way, the inactive universe left behind serves as a reminder of the intricate balance that governs the vast and varied structures of existence. The red dots surely represent some of the earliest galaxies, forming less than 1 billion years after the Big Bang. During this period, the universe was transitioning from the Dark Ages, a time when it was opaque and dominated by neutral hydrogen, to the epoch of reionization, when the first stars and galaxies began emitting light that re-ionized the surrounding medium. These red dots serve as direct evidence of this transformative era, marking the birth of structures that would later evolve into the galaxies we see today. The formation of these galaxies reflects the delicate interplay between gravity, dark matter, and baryonic matter. The gravitational pull of dark matter provided the scaffolding for ordinary matter to coalesce, ignite nuclear fusion, and form stars. These processes not only illuminated the universe, but also enriched it with heavier elements through supernovae, paving the way for the next generations of stars and galaxies. Observing the red dots allows scientists to trace how small, dense structures grew into the vast, organized systems of galaxies, clusters, and filaments that define the modern cosmic web. Active dots. The universe is vast and teeming with potential for discovering active galaxies beyond those already observed. Active galaxies, such as quasars, blazars, and Seyfert galaxies, are distinguished by their energetic cores, often fueled by supermassive black holes, accreting matter at their centers. These galaxies emit enormous amounts of radiation across the electromagnetic spectrum, making them some of the brightest and most dynamic objects in the cosmos. With advanced tools like the James Webb Space Telescope and ground-based observatories, the search for other active galaxies continues to unveil new possibilities, expanding our understanding of how galaxies evolve and interact with their environments. The presence of active galaxies in various stages of evolution suggests that many more remain undiscovered, particularly in the early universe. These galaxies offer a glimpse into the processes that shaped the cosmos during its formative years, as their intense activity often correlates with rapid star formation and the growth of black holes. By studying active galaxies, scientists can trace the intricate relationship between galactic nuclei and the broader cosmic structures they influence, such as gas flows, galaxy mergers, and the formation of new stars. Moreover, the detection of distant active galaxies opens doors to exploring conditions vastly different from those in our local universe. For instance, identifying galaxies with unusual spectra or extreme environments can reveal how diverse the mechanisms of galactic activity are. These discoveries not only deepen our knowledge of galactic behavior, but also help refine cosmological models, shedding light on the fundamental forces and interactions that govern the universe. The possibilities of discovering other active galaxies are vast and transformative. These energetic systems hold the keys to unraveling the mysteries of cosmic evolution, from the growth of supermassive black holes to the dynamics of early galaxy formation. As technology and observational techniques advance, the universe will likely continue to surprise us with its abundance of vibrant, active galaxies waiting to be explored. Thanks to the Webb Telescope, we have seen images light years away. Scientists and astronauts are overwhelmed to have more available pieces of evidence to look into. But the JWST started many years ago. It was reviewed frequently, restructured, replanned. Almost all processes it has gone through, even failures to launch. What to expect from the red dots in galaxies? The discovery of mysterious red dots in the early universe by the James Webb Space Telescope has opened a new frontier in our understanding of galaxy formation and evolution. These compact, red-tinted objects, dating back over 13 billion years, are thought to be among the first galaxies to form after the Big Bang. Their unique properties, such as their small size, intense brightness, and indications of active galactic nuclei, AGN, suggest that they harbor supermassive black holes in their centers. This raises intriguing questions about how such massive structures could develop so rapidly in the early universe. Future studies of these red dots will likely challenge and refine existing models of galactic evolution, shedding light on the interplay between black hole growth, star formation, and cosmic structure. Expectations are high that the red dots will reveal the processes that shape the first galaxies. Observing their chemical compositions and light emissions could provide insights into the conditions of the early universe, including the types of stars they formed and the role of dark matter in their development. Additionally, these observations might help answer broader questions about the universe's reionization period, a time when the first light from stars and galaxies altered the composition of the cosmos. As technology and analysis improve, the study of these red dots promises to uncover groundbreaking details about the universe's infancy, offering a clearer picture of how galaxies like our Milky Way emerged from the cosmic darkness. These findings will not only deepen our understanding of the cosmos, but also inspire new questions, ensuring that the exploration of these ancient galaxies remains a key focus in astronomy. The telescope mission. The James Webb Space Telescope is designed with 4 primary objectives: to investigate the light emitted by the earliest stars and galaxies that emerged in the universe following the Big Bang, to examine the processes involved in galaxy formation and their subsequent evolution, to enhance our understanding of star and planet formation mechanisms, and to explore planetary systems and the potential origins of life. These objectives are best achieved through observations in the near-infrared spectrum, as opposed to the visible light spectrum. Consequently, Webb's instruments are not equipped to detect visible or ultraviolet light, as is the case with the Hubble telescope. Instead, they possess a significantly enhanced capability for infrared astronomy. The telescope will be sensitive to wavelengths, which correspond to orange light and deep infrared radiation. Furthermore, Webb may be utilized to analyze the dimming light of star KIC 84628552, which was identified in 2015 and exhibits unusual light curve characteristics. Additionally, it will have the capability to detect methane in the atmospheres of exoplanets, enabling astronomers to assess whether the presence of methane could indicate biological activity. The launch, known as Ariane flight, occurred on time on December 25, 2021, using an Ariane 5 rocket from the Guyana Space Center in French Guiana. The telescope successfully received power. marking the start of a 2-week phase to deploy its components and head towards its target. It was released from the upper stage 27 minutes and 7 seconds after liftoff, beginning a 30-day process to adjust into a Lysajuice orbit around the L2 Lagrange point. The telescope was launched with slightly less speed than required for its final orbit and decelerated as it moved away from Earth, ensuring it arrived at L2 with just the right velocity to enter its orbit. It reached L2 on January 24, 2022, and the flight included 3 planned course corrections to fine-tune its speed and direction. The observatory could adjust for being too slow, but not for being too fast, as its sunshield must stay between the telescope and the sun to protect sensitive instruments, preventing any turns or thrust adjustments. Since an L2 orbit is unstable, the JWST needs to use fuel to maintain its halo orbit around L2, a process called station keeping, to avoid drifting away. It was designed with enough fuel for 10 years, but thanks to the precise launch and the first mid-course correction, it may have enough fuel to sustain its orbit for about 20 years. Space.com described the launch as flawless. The bigger telescope. The advent of future observatories like the Extremely Large Telescope, ELT, holds immense promise for expanding our understanding of the mysterious red dots in the early universe. Scheduled to begin operations in the coming years, the ELT, with its 39-meter mirror and unparalleled resolution, will provide unprecedented clarity in observing faint and distant celestial objects. This cutting-edge instrument is expected to complement the James Webb Space Telescope by capturing high-resolution data on the structure, composition, and behavior of these enigmatic galaxies. By resolving finer details of the red dots, the ELT could reveal their internal dynamics, such as star formation rates, gas distribution, and the influence of supermassive black holes at their centers. Additionally, the ELT's ability to observe across multiple wavelengths will enable deeper analysis of the chemical compositions and physical conditions within these galaxies. This could provide critical insights into the types of stars formed during the early universe and the role of dark matter in shaping these compact systems. Its capabilities in spectroscopic analysis will allow astronomers to study the interactions between stars, black holes, and the intergalactic medium, offering a more comprehensive understanding of how red dots contributed to cosmic ionization and the evolution of large-scale cosmic structures. The synergy between the ELT and other next-generation telescopes, such as the Square Kilometre Array, SKA, and Roman Space Telescope, will likely accelerate discoveries about red dots. Together, these instruments could confirm or challenge existing theories of galaxy formation, black hole growth, and the timeline of the early universe. In doing so, they will illuminate one of the most mysterious and formative periods of cosmic history, marking a new era in our exploration of the universe's origins. Redefining humanity's place in the cosmos. The revelation of the unknown red dots in the early universe by JWST has sparked immense public interest in astronomy and space exploration. These faint ancient galaxies, dating back to the universe's infancy, captivate imaginations with their profound implications about the cosmos and humanity's origins. The idea of peering 13 billion years into the past resonates with people of all ages, turning abstract scientific concepts into compelling stories about the formation of galaxies, the birth of stars, and the role of supermassive black holes. Such discoveries make the vastness of space more relatable, encouraging curiosity and wonder about the universe and our place within it. The visuals provided by JWST, such as detailed images of these red dots amidst cosmic structures, have become iconic, capturing the attention of media and audiences worldwide. These images transcend the scientific community, inspiring artists, educators, and the general public to engage with space science. Educational outreach programs and media coverage around these findings fuel discussions about astronomy, encouraging students and aspiring scientists to pursue careers in the field. Moreover, the red dot discoveries underscore the importance of investing in advanced technology and international collaborations, fostering public support for future space missions and observatories. The red dot discoveries not only expand humanity's scientific knowledge, but also inspire a deeper appreciation for the mysteries of the universe. By making distant cosmic phenomena accessible and engaging, They bridge the gap between complex scientific exploration and public curiosity, ensuring that the wonder of the cosmos continues to captivate and unite people across the globe. The uncovering of ancient galaxies, such as these vast red dots, profoundly reshapes humanity's understanding of its place in the universe. These ancient cosmic structures, formed billions of years ago, serve as a reminder of the universe's immense scale and age, highlighting how small and fleeting human existence is in comparison. The light from these galaxies, traveling for more than 13 billion years to reach us, offers a direct glimpse into a time shortly after the Big Bang, bridging the gap between the universe's origins and our present reality. This connection to such a distant past instills a sense of awe and humility, reminding us of the intricate and vast cosmic web that preceded and encompasses our existence. These discoveries also challenge humanity to rethink its significance in a universe that is not only ancient, but also boundless. If these galaxies existed in the infancy of the cosmos, what other phenomena might exist in parts of the universe we have yet to observe? This question fuels philosophical inquiry into whether humanity's role is one of mere observers or active participants in uncovering the mysteries of existence. Moreover, the realization that the same fundamental forces and elements that shaped these ancient galaxies are present within us fosters a profound sense of interconnectedness with the cosmos. Ultimately, the unveiling of ancient galaxies deepens our curiosity about the origins of life, the nature of time, and the potential for other intelligent civilizations. It invites humanity to approach its place in the cosmos with wonder and responsibility, inspiring both scientific exploration and philosophical reflection. These findings affirm that while our physical presence in the universe may be small, our capacity to seek and understand the vastness of existence is a defining characteristic of our shared humanity. In the next years to come, who knows what kind of red dots we'll get to witness? You reached the end of the video. Stay tuned for more astronomic content like this. See you in the next one.